Welcome to the Deep Dive, the show where we take a mountain of information and extract the nuggets of knowledge you need to be truly well-informed. Have you ever paused to consider the silent, remarkable work happening behind the scenes of your everyday tech?
You mean like how your phone somehow understands your spoken commands?
Exactly. Or how, with a single click, a complex foreign web page instantly translates into your native language. These aren't just convenient features, they're the seamless, often unseen marvels powered by something called natural language processing, or NLP.
It's true. We interact with it constantly, probably without even thinking about it. Yet most of us take it for granted.
Definitely.
But behind those effortless interactions lies one of the most fascinating and, frankly, complex fields in artificial intelligence.
Today we're taking a deep dive into natural language processing. We'll unpack exactly what it is, how it actually functions, trace its surprisingly tumultuous journey through history, and discover why it's quietly reshaping almost every corner of your digital life and extending far beyond.
Yeah, our mission here is really to navigate this incredibly multidisciplinary field, tracing its path from, well, ambitious academic dreams way back when, to the indispensable technology it is today.
We'll explore its foundational components, delve into its historical shifts and breakthroughs, highlight its amazing real-world applications across a dizzying array of industries.
And then critically examine the significant challenges and, importantly, the ethical considerations that come with teaching machines to communicate like us.
Right. By the end of this deep dive, you'll have a clear shortcut to truly understanding the science of how humans and computers talk to each other.
You'll not only grasp what makes your conversational AI tick, or how that translation tool works its magic.
But you'll also gain a crucial perspective on both the immense opportunities and the serious responsibilities that come with giving machines the power to understand our language. Get ready for some genuine aha moments.
Moments that might completely change how you view your everyday tech.
So let's jump in. When we talk about NLP, what exactly are we talking about? It sounds a bit like something from a sci-fi movie, maybe, but it's very much shaping our present.
It absolutely is. At its core, NLP is a dynamic and truly multidisciplinary field. It sits right at the intersection of artificial intelligence, AI, computer science, and linguistics.
Okay.
You can think of it as the ultimate language bridge, or maybe even a kind of universal translator for computers. Its fundamental objective is to give machines the ability to understand, interpret, manipulate, and crucially, generate human language.
And that covers everything, like text and speech.
Both, yeah. Written, text, and spoken words.
So, if I'm understanding this, the ultimate goal is to bridge that enormous communication chasm between the superstructured, hyper-logical world of computer code
Right.
and our human language, which, let's be honest, is often fluid, nuanced, and frequently frustratingly ambiguous. Is that the biggest challenge?
That's precisely the central challenge. Human language isn't a static, predictable set of rules like, say, Python or Java.
Not at all.
It's a rich, living tapestry of dialects, slang, jargon that's constantly evolving, and even frequent grammatical deviations, mistakes or just quirks that make formal rules really difficult to apply consistently.
So an effective NLP system has to be engineered not just to follow rules, but to navigate all that inherent variability.
Exactly. It has to correctly interpret intent and meaning despite these complexities. It's a truly monumental undertaking for a machine, frankly.
And this isn't just an academic exercise, is it? It's really making a difference in the real world. I mean, businesses are leveraging NLP to automate a vast array of tasks.
Oh, definitely. You're talking about things like processing and archiving huge volumes of documents automatically,
Right.
analyzing customer feedback from call center recordings or written reviews to understand sentiment,
Right.
and deploying automated systems, chatbots to answer common questions. The aha here for listeners is realizing how much of their daily interactions with technology are silently powered by this. It's about making technology feel more intuitive and seamless.
Now, what's fascinating here, I think, is how NLP achieves its goals. You mentioned it involves a kind of triad of language technologies.
Yes, that's a good way to put it. We use NLP as the overarching umbrella term for the complete pipeline, from human language input all the way to machine-generated output.
Like a chatbot handling the whole conversation.
Exactly. Think of a conversational AI, like that customer service chatbot you might interact with online. That entire interactive flow is managed by an NLP system. But underneath that umbrella are two distinct yet complementary components: natural language understanding, or NLU, and natural language generation, NLG.
Okay, let's break those down. NLU, natural language understanding. This is where the machine tries to figure out what you're saying, right? How does it manage that incredibly complex task of deciphering our messy human language?
NLU's primary objective is to deconstruct language to determine its underlying meaning and your true intent. It takes unstructured text or speech and converts it into a structured, machine-readable format that an algorithm can actually act upon.
So it's more than just recognizing words.
Much more. It involves a deep analysis of linguistic components. Things like syntax, which is the grammatical structure of a sentence,
Uh-huh.
semantics, which is the literal meaning of words and their combinations,
Okay.
and pragmatics, which is the intended meaning derived from the broader context. It's like breaking down a complex puzzle into its individual pieces, then understanding how they fit together and what the picture is actually trying to convey.
Can you give us an example of NLU in action that we might actually encounter? Something concrete.
Certainly. When you ask a virtual assistant, maybe on your phone, find me a recipe for vegan lasagna, the NLU component is the one parsing that request.
Right.
It identifies your core intent, which in machine terms might be recipe, and then extracts the key entities, in this case, vegan lasagna. It understands what you want to do and what it's about, even if you phrased it casually.
Okay, that makes sense. And once it understands, it has to respond, right?
Right.
That's where natural language generation, NLG, takes over. It's the machine's turn to speak, so to speak.
Exactly. NLG is the complementary output or expression phase. It takes the structured data or the system's internal decision, like having found that perfect vegan lasagna recipe, and transforms it back into coherent, contextually appropriate human language, either as text on a screen or synthesized speech.
So it figures out how to say it.
Precisely. It tackles the challenge of how a machine should articulate its response. So, to continue our example, after the system identifies a suitable recipe, the NLG component formulates the reply. I found a popular recipe for vegan lasagna from the Modern Chef. Would you like me to send it to you? Nice and natural.
So NLU and NLG are these synergistic engines that truly power NLP, enabling a fluid bidirectional communication loop. The true aha here is realizing that every seamless back and forth you have with a machine isn't magic.
Definitely not magic.
It's a meticulously engineered dance between two distinct AI brains. One that works tirelessly to understand your messy human input, and another that artfully crafts the machine's perfectly phrased response.
That's a great way to put it. It's the secret to that surprisingly natural conversation we sometimes experience.
Yeah.
And stepping back a bit, it's crucial to understand where NLP fits within the broader landscape of technology and academia. It doesn't exist in a vacuum, you know?
Right, correct.
NLP is widely recognized as a core subfield of artificial intelligence because, simply put, the ability to understand and use language is a fundamental characteristic of human intelligence.
What makes us in many ways.
Exactly. AI provides the overarching goal of creating intelligent systems, and NLP provides the specific mechanisms for achieving this critical aspect of intelligence, communication.
So AI is the big picture, and NLP is a vital piece of that puzzle. But what about machine learning and deep learning? We hear those terms thrown around constantly. How do they relate to NLP?
That's a really important connection. In its modern form, NLP is fundamentally an application of machine learning. Early NLP systems were very different. They relied on handcrafted rules, where human experts literally programmed every grammatical rule and exception they could think of.
That sounds painstaking.
Oh, incredibly. But the field was revolutionized by machine learning algorithms that could learn linguistic patterns automatically from vast amounts of data. For instance, supervised learning trains models on massive data sets where inputs are paired with correct outputs.
Like emails labeled spam or not spam.
Exactly. Thousands, millions of examples, allowing the machine to discover patterns on its own. More recently, deep learning, which is a powerful subset of machine learning using multi-layered neural networks, has become the dominant paradigm.
Right, neural nets.
Deep learning models can learn incredibly complex and abstract representations of language, achieving state-of-the-art performance on nearly every NLP task you can imagine.
That makes a lot of sense. So it really shifted from a very manual, rule-based approach to one where the machines learn directly from data. But then there's also computational linguistics. Is that just another name for NLP, or is it different?
That's a nuanced but important distinction. Computational linguistics, or CL, is primarily a scientific discipline. It's focused on studying language through a computational lens, developing formal models and theories to understand the fundamental structure and properties of human language.
So it's more theoretical, asking the how does language work questions.
Precisely. It asks deep theoretical questions like, how can we computationally model the underlying principles of language? In contrast, natural language processing is more of an engineering discipline. It's concerned with building practical software and systems that can perform useful tasks with language, often drawing upon the theoretical insights and methods pioneered by computational linguists.
So NLP asks, how can we build a system that translates languages effectively?
Mhm.
Or how do we make a chatbot understand a customer's complaint? That sort of practical application.
Exactly. CL is the science, and NLP is more the application or the engineering side. That's a great way to put it. And the evolution of NLP has been marked by a dynamic and sometimes, well, contentious relationship with linguistics. The field's origins were deeply rooted in linguistic theory, with early pioneers attempting to explicitly codify the rules of grammar and syntax. They treated language processing almost like a problem of formal logic.
But language isn't always logical.
Not at all. The immense complexity and irregularity of real-world language proved incredibly difficult to capture with those handwritten rules, which led to a major paradigm shift. The statistical and neural revolutions pushed the field decisively towards an engineering-centric paradigm.
Where performance became key.
Performance on quantitative benchmarks became the primary measure of success, sometimes, arguably, at the expense of linguistic plausibility. For a time, it seemed that with enough data and computational power, explicit modeling of linguistic principles was becoming almost obsolete.
But I've heard whispers about a third turn emerging now, a recognition that maybe we can't just keep throwing more and more data at the problem without understanding the why, what's going on there.
That's a great question, and it's where things get really interesting right now. Despite achieving often superhuman performance on many specific tasks, today's state-of-the-art models are still frequently criticized for what researchers call brittle semantic competence.
Brittle competence,
Okay.
meaning they break easily under pressure.
Sort of, and a profound lack of true human-like reasoning. They excel at recognizing statistical patterns and generating coherent text, but they can struggle with genuine comprehension, common sense inference, and a robust understanding of abstract concepts.
I don't really understand the human sense.
That's the argument. This has led to a growing recognition within the research community that for the next wave of breakthroughs, we may need a renewed engagement with linguistics and cognitive science. There's an increasing call for a new alliance
Okay.
where theoretical insights from these fields can guide the development of next-generation AI systems, helping to imbue them with the structural and cognitive foundations they currently lack.
So the future isn't just bigger models, but smarter models informed by language science.
That appears to be the direction. The future of NLP, therefore, appears to lie not in a victory of engineering over linguistics or vice versa, but in a sophisticated synthesis of the two, leveraging the immense power of large-scale, data-driven learning while being guided by a principled understanding of language and cognition.
That potential for a deeper synthesis between engineering and the very science of language sounds truly fascinating. Now, let's take that journey through time and see how NLP has actually evolved. It's a compelling narrative, isn't it? Big ambitions, surprising setbacks, and remarkable ingenuity.
Indeed. We can broadly categorize this evolution into three distinct eras, each fundamentally driven by shifts in our theoretical understanding of language, the computational power available, and, critically, the sheer amount of data we could access. We start with the symbolic era, spanning roughly from the 1950s to the 1980s.
And this era really began with Alan Turing, didn't it? His famous Turing test in 1950 placed language squarely at the heart of the quest for artificial intelligence.
It really did.
He proposed that if a machine could engage in a written conversation so convincingly that a human couldn't tell if they were talking to a machine or another human, then it could be considered intelligent. Language as the benchmark.
Absolutely. That foundational idea set the stage for the symbolic approach, which believed that true intelligence could be achieved by manipulating symbols according to explicit, hand-coded rules, essentially, teaching computers human logic and grammar directly.
And the first big goal was machine translation.
That was the first major ambition that truly galvanized the field and brought significant funding. This was a challenge of immense geopolitical importance in the post-World War II Cold War era.
And there was this huge wave of optimism early on, right? I've heard about the 1954 Georgetown IBM experiment. That made waves.
That's right. It was a groundbreaking public demonstration where a machine successfully translated over 60 Russian sentences into English. A small number, but huge at the time. This sparked immense optimism, and researchers at the time boldly, and quite prematurely, predicted that machine translation would be fully solved within just a few short years.
Famous last words.
Pretty much.
Yeah.
The sheer complexity of human language, with all its idioms, nuances, and ambiguities, proved far greater than anticipated, and progress quickly stagnated. This widespread disillusionment eventually culminated in the influential 1966 ALPAC report.
Ah, yes, the LPAC report. That's a report that concluded a decade of research failed to meet expectations, leading to drastic funding cuts.
Right.
And what's known as the first AI winter, wasn't it? A period of reduced research and funding that lasted nearly 2 decades.
Precisely. So early ambitions certainly met a dose of cold reality, but it wasn't all just setbacks. This era still laid crucial intellectual groundwork. Linguist Noam Chomsky's 1957 work, Syntactic Structures, for example,
Huge influence.
introduced generative grammar, a formal, rule-based system for describing language structure, which became a cornerstone of early NLP research. Chomsky emphasized the critical need for machines to be able to distinguish between grammatically correct sentences and nonsensical ones, which is harder than it sounds.
And we also saw some iconic systems emerge during this time. Eliza, the chatbot that simulated a psychotherapist, comes to mind. It always struck me as surprisingly effective for its time, almost unnerving.
Eliza, created by Joseph Weizenbaum in 1966, was truly iconic. It used surprisingly simple pattern-matching techniques, essentially reflecting questions back to create a convincing illusion of understanding and empathy. It showed how even clever rule-based systems could elicit human-like interaction.
And then SHRDLU, that was more complex.
Yes, SHRDLU in 1970, developed by Terry Winograd, was a more complex system operating in a constrained blocks world, a simulated world with blocks on a table. SHRDLU could understand and execute intricate natural language commands like pick up the red block and put it on the blue pyramid, and its ability to reason about its actions within its limited domain, answering questions about why it did something, was a landmark achievement.
So the symbolic era was really defined by meticulous manual work. It was all about humans trying to codify language laws into explicit rules and conceptual ontologies for machines to follow. A true intellectual endeavor, but maybe ultimately limited.
That's a perfect summary. Then, from the late 1980s and extending into the 2010s, we witnessed a profound paradigm shift, the statistical revolution. This was a dramatic departure from those handcrafted rules towards machine learning algorithms that could learn linguistic patterns automatically from massive bodies of text known as corpora.
This sounds like a huge step forward, moving away from all that painstaking manual programming. What really drove this shift? Was it just better computers?
Better computers were definitely part of it. Two concurrent developments created the perfect storm. First, an exponential increase in computational power, making complex statistical calculations feasible.
Right.
And second, the explosion of digital text made available by the internet. Suddenly there was data. For the first time, massive data sets were available to train statistical models effectively.
So the data caught up with the computing power.
Exactly. This era was dominated by probabilistic methods. Algorithms like hidden Markov models, or HMMs, became standard for tasks such as part-of-speech tagging, identifying if a word is a noun or a verb, and speech recognition. Decision trees and other statistical classifiers were widely used for tasks like text categorization, like spam filtering.
So the focus really shifted from trying to define formal linguistic rules to simply measuring how accurate the system was on real-world data. It was all about performance metrics.
Exactly. Performance benchmarks became the driving force, and foundational techniques for text representation emerged during this time that are still relevant today. Concepts like the bag of words model.
Which just counts words, right? Ignores order.
Pretty much. It represents a document as an unordered collection of its words, ignoring grammar or word order, but noting word frequency. Simple, but effective for some tasks. And term frequency inverse document frequency, or TF-IDF.
Okay, what's that?
TF-IDF weights words by how important they are to a specific document relative to an entire collection of documents. So a word that appears often in one document but rarely in others gets a high weight.
Ah, so it finds the distinctive words.
Exactly. The so what of this era, the real nugget here, is that it made NLP systems scalable and far more robust to the inherent variability and messiness of real language by letting the data drive the learning. It moved beyond the brittleness of trying to capture every single exception with handwritten rules.
And that brings us to the current era, the neural era, from the 2010s to the present. This is where deep learning really took hold, marking a revolution as significant as the shift from rules to statistics. This is the era of the AI we're interacting with today, the LLMs and chatbots.
It truly has been transformative. A pivotal breakthrough that set this era in motion was the development of word embeddings, most famously exemplified by Tomasz Mikołaj's word-to-vec model in 2013.
Word embeddings. These are the numerical representations of words, right?
Yes, but unlike the sparse, count-based TF-IDF vectors, these are dense, low-dimensional numerical vectors that manage to capture rich semantic context, meaning.
This is where it gets truly fascinating for me. My understanding is that these embeddings allow words with similar meanings to be positioned close together in a mathematical space.
Exactly.
And even relationships can be captured mathematically, like the famous example, king minus man plus woman, results in a vector very close to queen. Is that right?
That's the perfect way to explain it. It showed that meaning could be represented geometrically, which provided a much richer and more nuanced way for machines to represent word meaning.
Wow.
Following this, recurrent neural networks, or RNNs, and their more sophisticated variant, long short-term memory, or LSTM networks, became state-of-the-art for sequential data like text.
Because they have memory.
Precisely. Their ability to maintain a memory of previous inputs made them highly effective for tasks like language modeling and machine translation, where sequence matters.
But the real game changer, the watershed moment that truly set the stage for our current AI boom, seems to be the transformer architecture. I remember that paper, Attention is All You Need, from 2017. What made it such a breakthrough?
That paper and the transformer architecture it introduced are indeed monumental. The transformer's key innovation was the self-attention mechanism.
Self-attention. What does that let it do?
Instead of processing words one by one, like an RNN, this mechanism allowed models to weigh the importance of all words in an input sequence simultaneously. It could look at the whole sentence at once, in a sense.
So it understands context better.
Fundamentally better. This fundamentally changed how models captured complex, long-range dependencies within text relationships between words far apart in a sentence. And crucially, it enabled much greater parallelization during training.
Making it faster to train bigger models.
Much faster and more efficient. It was like suddenly giving the computer a way to see the entire sentence at once, understanding how different parts related, rather than just processing it linearly, step by step.
And the transformer directly paved the way for what we now call large language models, or LLMs. We're talking about models like Google's BERT and OpenAI's GPT series, both first released around 2018. These are the giants we hear so much about today.
Exactly. These massive models are pre-trained on internet-scale text corpora, just unimaginable amounts of text.
So they learn language from reading the web, basically.
In a sense, yes. This allows them to acquire a broad and deep understanding of language structure, grammar, and even extensive world knowledge embedded in that text. They can then be fine-tuned with smaller, task-specific data sets to achieve state-of-the-art performance on a vast array of NLP applications, everything from question answering to summarization, with minimal additional training.
So they have a general understanding, and then you specialize them.
Precisely. The overall significance of this neural era and the biggest aha moment is that it has revolutionized not just the capabilities, but also the accessibility of powerful NLP, leading directly to the advanced AI systems we interact with every single day.
It's truly incredible to see how far we've come. Now, let's pull back the curtain and talk about what happens inside the machine. How does raw text actually get transformed into something a computer can understand? We're talking about the NLP pipeline, right? The steps involved.
That's a great way to think about it. To process human language, raw text undergoes a methodical series of transformations known as the NLP pipeline. It systematically deconstructs language from its unstructured form into a structured representation that machine learning models can interpret and analyze.
Like an assembly line for language.
You can really visualize it as a cascade of increasing abstraction. It starts with the most basic elements, characters, and words, and progressively organizes them into grammatical structures, eventually culminating in the extraction of high-level meaning. Each step builds upon the output of the previous one.
Okay, step-by-step refinement. But you mentioned earlier that modern systems are blurring these lines. How so? With things like transformers.
That's a key insight into modern NLP. While the conceptual tasks of the pipeline remain essential for understanding what a model must achieve, modern end-to-end neural architectures, especially transformers, often learn these necessary syntactic and semantic features implicitly within their deep layers.
So they don't necessarily have separate modules for each step anymore.
Not always explicitly, no. They learn to do much of it internally rather than executing them as discrete sequential steps like in classical NLP. This represents a significant shift. Now, the machine figures out many of these steps on its own during training.
Okay, but conceptually, let's start with the first, foundational stage, data preprocessing. This is where we clean and structure the raw text, making it ready for analysis. You can't feed raw web text straight in, can you?
Generally not, no. Its core purpose is to transform raw text from a simple string of characters into a format that's actually suitable for algorithmic analysis. The first fundamental step here is tokenization.
Breaking it down into pieces.
Yes, this process breaks down a continuous stream of text into smaller, discrete units called tokens. These tokens serve as the basic building blocks for all subsequent analysis.
So if I say NLP is powerful, it would be tokenized into separate pieces. NLP is powerful, and then the period punctuation mark. Is that word tokenization?
That's the most intuitive approach, yes, simply splitting by spaces and punctuation. But that simple approach can struggle with things like hyphenated words, like state of the art.
Right.
Or contractions, like don't, or even languages that don't use spaces between words at all, like Chinese or Japanese.
Okay, so word splitting isn't perfect. What else is there?
Well, there's also character tokenization, which breaks text down to individual characters. That results in a very small vocabulary, which is good, but unfortunately it loses most of the semantic meaning associated with whole words.
And then there's subword tokenization, which I understand is the modern standard, especially with LLMs like GPT. How does that work without getting too bogged down in the technical details?
Right. Without going deep into algorithms like byte pair encoding or word piece, the key aha of subword tokenization is that it strikes a clever balance. It breaks text into frequently occurring subword units or morphemes rather than just whole words.
Like prefixes and suffixes.
Sometimes, yes, or common parts of words. This approach elegantly handles rare words, misspelled words, or even brand new words, what we call out-of-vocabulary OOV words, by representing them as a sequence of known subwords it has seen before.
So it can handle novelty.
Exactly. For instance, an uncommon or new word like untokenizable might be broken down into pieces like unhashtag token, hashtag tagizable, where the hashtag indicates it's part of a word. It's like finding the core Lego bricks within even the most unique custom-built word, ensuring the system can always build something recognizable and meaningful.
That's clever. Okay, beyond tokenization, what else happens in this crucial pre-processing phase? Cleaning things up.
We also have normalization, which typically includes stemming and lemmatization. This is all about ensuring that different forms of the same word are treated as equivalent by the system.
Like run, running, ran.
Precisely. Stemming is a crude, fast, rule-based process that basically chops off prefixes or suffixes to get to a word's stem. It's quick, but often results in non-dictionary words. For example, studies, studying, and student might all be reduced to a common stem like studi.
Which isn't actually a word. It sounds a bit blunt. What's the more sophisticated option for normalization?
That would be lemmatization. It's a more sophisticated dictionary-based approach that considers the part of speech of a word, whether it's a noun, verb, etc., to return its canonical form, or lemma.
The dictionary-based form.
Yes. For example, the verb studies would be correctly lemmatized to study, and the adjective better would be mapped to its lemma, good. It's more computationally intensive, requires more resources, but yields far more accurate and meaningful base words.
Makes sense.
And finally, a common step, though not always used depending on the task, is stop word removal. This filters out high-frequency words like a and the, is, and but, words that often contribute very little semantic value on their own.
Why do that?
It reduces the dimensionality of the data, makes processing faster, and allows the system to focus on the more meaningful terms in the text.
So these seemingly simple steps, tokenizing, normalizing, maybe removing stop words, are absolutely crucial for the computer to even begin understanding your raw input.
Yeah.
Like you said, sorting the Legos before building. They're the silent foundation.
Exactly. Once the text is cleaned and tokenized, the pipeline moves to syntactic analysis. This aims to understand the grammatical structure of sentences and the relationships between the words.
How the sentence fits together.
Right. The first crucial step here is part of speech, POS tagging. which assigns a grammatical category like noun, verb, adjective, adverb, preposition to each token identified earlier.
And this is so important for disambiguation, right? Like distinguishing book as a noun versus a verb. It's a very human way to differentiate meaning based on how a word is used.
Precisely. It helps the machine know whether you mean I read a book or I need to book a flight. Without PS tagging, simple word lookups would be almost useless because words mean different things in different grammatical roles.
Okay. And after PS tagging?
After PS tagging, we have parsing, also known simply as syntactic analysis. This involves determining the full grammatical structure of a sentence, typically output as a tree-like representation, showing how phrases and words relate.
Why is parsing so important?
Accurate parsing is essential for tasks requiring a deep understanding of sentence structure, such as machine translation, complex question answering, or extracting precise relationships between entities.
Are there different kinds of parsing that are important for the machine to really understand structure? Different ways to build that tree?
There are two primary approaches that are worth noting conceptually. First, constituency parsing, sometimes called phrase structure parsing. This breaks a sentence down into its constituent phrases, like noun phrases, NP, and verb phrases, VP, showing a hierarchical nested structure like those nesting dolls of grammatical components.
Okay, showing the phrases.
Then there's dependency parsing. This focuses more directly on the grammatical relationships between individual words. It creates a directed graph where edges represent specific grammatical relationships, like which word is the subject of a verb, or which adjective modifies which noun.
So it focuses on word-to-word links.
Exactly. This approach is particularly effective for languages with more flexible word order than English, where grammatical roles aren't always tied to position. The so what here, the key takeaway, is that this is where the machine starts to understand how words fit together to form coherent thoughts, not just what the individual words are. It begins to grasp the underlying scaffolding of language.
So we've broken down the text, cleaned it up, understood its grammatical structure, like the skeleton. What's the final stage of analysis where the machine really tries to grasp the deeper meaning, the conceptual essence of the text, the flesh on the bones?
That's semantic analysis, the final stage in this conceptual pipeline, moving beyond grammar to interpret the actual meaning conveyed by the text. A cornerstone technique here is named entity recognition, or NER.
Recognizing names and places.
Names, places, organizations, dates, monetary values, product names, yes. NER is a powerful tool for information extraction. It identifies and classifies these named entities, which are essentially real-world objects with proper names.
Like in that sentence, in 2022, Apple's CEO Tim Cook announced the new iPhone in Cupertino. NER would pick out all those specific pieces of information you just mentioned.
Exactly. It identifies 2022 date, Apple organization, Tim Cook person, iPhone product, and Cupertino location. The real nugget here is how NER effectively transforms unstructured, free-flowing text into highly structured, queryable data, making it easy for machines to find specific facts.
That's incredibly useful. What else happens in semantic analysis?
Then there's word sense disambiguation, or WSD. This specifically tackles words with multiple meanings, like our earlier bank example. WSD determines the correct meaning or sense of such a word based on its surrounding context. Is it a financial bank or a riverbank?
Context is key there.
Absolutely. And finally, another critical task is coreference resolution. This identifies all the expressions within a text that refer to the same real-world entity. Think pronouns and repeated references.
Okay, so in a sentence like, Jane went to the store, she bought a new laptop, it was on sale. Core reference resolution would be the process of linking she back to Jane and it back to a new laptop.
Yeah.
Understanding what she and it refer to.
Precisely. This is absolutely crucial for understanding the flow of discourse over multiple sentences or even paragraphs. Without it, the system loses track of who or what is being discussed. These semantic steps are truly crucial. They allow systems to go beyond simply processing individual words to actually understanding what you're talking about and who or what you're referring to across an entire conversation or document. They are the bedrock of machine comprehension.
It's truly fascinating to see how the machine breaks down language into these digestible parts, layer by layer. Now let's see NLP in action. And one of the most visible applications that most of us interact with daily is conversational AI. We're talking about customer service chatbots and voice assistants like Apple's Siri or Amazon's Alexa. These are specifically designed to mimic natural conversation.
They are absolutely ubiquitous now, aren't they? And it's important to highlight how modern systems have moved far, far beyond the rigid, rule-based chatbots of the past.
Oh yeah, those were frustrating.
They were limited to responding to a narrow set of pre-programmed commands. Those old systems often failed with an annoying "I don't understand" message when faced with unexpected user input. These new systems operate through a remarkably sophisticated multi-stage pipeline, from your initial query to their final response.
Okay, let's unpack this pipeline for conversational AI. If I'm using a voice assistant, how does it go from hearing my voice to actually giving me an answer? It feels instantaneous.
Well, it starts with input processing. For voice assistants, this first involves automatic speech recognition, or ASR.
Speech to text.
Right, which accurately converts your spoken language into digital text. Once it's in text form, the input undergoes those standard pre-processing steps we just discussed, like normalization to lowercase, tokenization to prepare it for deeper analysis.
Got it. Then the understanding part.
Then comes the critical brain of the system, natural language understanding, or NLU, where the chatbot deciphers your meaning. This NLU component performs two primary subtasks we touched on: intent recognition.
Figuring out what I want.
Exactly. Identifying the user's primary goal. For example, set a timer for 10 minutes would be precisely recognized as the set timer intent. And entity recognition.
Finding the key detail.
Yes, extracting specific pieces of information needed to fulfill that intent, like identifying 10 minutes as the duration entity in our timer example.
So it understands what I want to do and what specific information I'm giving it. But what happens next to keep the conversation going smoothly? Like remembering previous things I've said. That seems crucial for it to feel like a real conversation.
That's where dialogue management comes in. Think of it as the conversation's conductor. This component maintains the state of the interaction, meticulously tracks context across multiple conversational turns.
So it remembers what we talked about.
Yes, and then determines the system's next appropriate action based on that history and the current input. This is the magic that allows you to ask a follow-up question like, and add a reminder to check the oven, with the system understanding that the reminder is directly related to the previously set timer. It's absolutely essential for creating coherent, multi-turn conversations rather than just disconnected one-off queries.
That makes a huge difference.
Yeah.
And then finally, it speaks back.
Finally, there's response generation, or NLG. After the dialogue manager decides on an action, like, okay, I need to confirm the reminder, NLG formulates a human-readable response. For voice assistants, this generated text is then passed to a text-to-speech, or TTS engine.
Like the ones used to make this deep dive.
Exactly like those.
Yeah.
Which synthesizes the audible voice you hear.
So it's like a highly skilled interpreter who not only hears your words, but instantly understands your intent, meticulously remembers the entire conversation's context, and then formulates a perfectly coherent, relevant reply. That analogy really makes it clear how complex it is, but how seamless it feels when it works well.
And what's truly fascinating here, and a massive aha for most people, is the transformative impact of large language models, or LLMs, on conversational AI. Models like OpenAI's GPT-4 and Google's Gemini have profoundly revolutionized both the NLU and NLG stages, pushing the boundaries of what these systems can do.
This is why our interactions with AI assistants feel so much more natural and capable now, isn't it? It's not just a little better. It feels fundamentally different than just a few years ago.
Absolutely. Instead of relying on separate, narrowly trained classifiers for intent and entity recognition, LLMs possess a much more holistic and nuanced understanding of language, derived from their vast pre-training on enormous text datasets.
So they just get language better overall.
In a sense, yes. This allows them to interpret complex, ambiguous, or even poorly phrased user queries with far higher accuracy and flexibility. They're less brittle. And on the output side, their generative capabilities represent a monumental leap.
So.
Instead of being confined to pre-scripted templates or fill-in-the-blank responses, LLMs can generate novel, creative, and highly fluent text from scratch. This allows for responses that are truly personalized and deeply context-aware.
So they can actually write new sentences tailored to the situation.
Exactly. This has given rise to a new generation of AI agents, or generative AI bots, that can autonomously handle far more complex and open-ended conversational tasks than ever before, asking follow-up questions, clarifying, synthesizing information.
That's truly game-changing. To really drive home this evolution, let's look at a case study. The journey from those frustrating, limited, rule-based help desks of the past to the intelligent virtual assistants we use today. It's a night and day difference.
It really is. Early commercial chatbots were almost exclusively rule-based, operating on very simple if-then logic and keyword matching. Any deviation from the expected script would typically result in a canned failure message like, "I'm sorry, I don't understand," which, as you can imagine, quickly led to user frustration and abandonment.
We've all been there. Trying to talk to those old chatbots felt like trying to navigate a maze with only one correct path, and you kept hitting dead ends. But now, NLP-powered chatbots are deployed across virtually every industry, and they're genuinely useful much of the time.
Indeed. In finance, they seamlessly handle balance inquiries and simple transactions. In healthcare, they can schedule appointments and answer common patient questions, freeing up staff. In e-commerce, they expertly track orders and provide tailored product recommendations based on your history.
And they work all the time, right?
These systems can operate 24/7, understand multiple languages, and crucially, they learn from interactions to continuously improve over time. The value proposition for both you, the user, and for businesses is twofold.
Okay.
They dramatically improve the customer experience by providing instant, personalized support, reducing wait times, and they generate significant operational efficiencies by automating routine queries, which reduces costs and frees up human agents to focus on more complex, high-value interactions that really need a human touch.
So think about your last online customer service interaction. Chances are an NLP-powered chatbot made it smoother and faster without you even realizing the complex dance happening behind the scenes.
No.
It's a testament to how far this technology has come. Conversational AI is definitely highly visible, but another absolutely crucial application of NLP, which has seen enormous advancements, is machine translation. It's truly bridging global divides in ways that were once unimaginable. Reading websites, communicating across borders.
Machine translation, or MT, was one of the earliest and most ambitious goals of NLP, dating way back to the post-World War II era, as we mentioned. Its evolution actually perfectly mirrors the major paradigm shifts within the NLP field itself. We've seen a clear progression from rule-based systems to statistical models and now to neuro-machine translation.
So what was the rule-based machine translation, or RBMT, approach like? That sounds like something from the symbolic era we discussed. Very structured.
You're spot on. That was the earliest approach, dominant in the symbolic era. It involved linguists and programmers painstakingly handcrafting extensive sets of grammatical rules and bilingual dictionaries for each language pair.
So like French to English rules, German to English rules?
Exactly. They tried to parse the source text, analyze its syntactic structure using those rules, transfer the meaning, and then reconstruct a sentence in the target language using its rules. However, the sheer complexity and the countless exceptions in human language made this approach incredibly brittle, very expensive to build and maintain, and consistently prone to producing awkward, literal, and often grammatically incorrect translations.
Like trying to translate a poem word for word with a dictionary, you lose all the nuance.
Precisely. And then came the statistical machine translation, or SMT, riding the wave of the statistical revolution. This must have been a significant improvement, right? Using data instead of rules.
Yes. SMT became the dominant paradigm from the 1990s through the mid-2010s. It abandoned those explicit linguistic rules in favor of learning from data. SMT models worked by analyzing massive parallel corpora.
Meaning text translated by humans.
Exactly, huge collections of text that had been professionally translated. By analyzing these, SMT systems learned the statistical probabilities that a word or phrase in the source language corresponds to a word or phrase in the target language.
So it learned patterns of correspondence.
Right. While a significant improvement over RBMT and fluency, SMT systems often struggled with capturing long-range contextual dependencies and maintaining overall coherence, as they typically translated text in smaller, isolated chunks, often sentence by sentence, or even phrase by phrase independently. And now, we're firmly in the era of neural machine translation, or NMT. This is the current state of the art. What powers Google Translate and similar tools today? What's the key difference here that made it such a breakthrough in quality?
NMT leverages deep neural networks, specifically sequence-to-sequence models, to perform translation. The absolute key difference, the real aha moment for translation, is that NMT models process the entire source sentence as a single input to generate the translation.
The whole sentence at once.
Conceptually, yes. This allows them to capture context, fluency, and grammatical nuances far, far more effectively than their predecessors, which looked at smaller pieces. A landmark event showcasing the superior quality was Google Translate's public switch from an SMT-based system to a proprietary NMT system back in 2016.
I remember that. The improvement was noticeable almost overnight.
It was. Millions globally could see the difference. Each shift in these paradigms, rules, statistics, neural nets, represented a fundamental change in how machines learned language for translation, pushing closer and closer to natural human translation quality.
That's a huge leap in quality.
Yeah.
So how does NMT actually work inside? What's the architectural idea that lets it process entire sentences so effectively? You mentioned sequence to sequence.
Modern NMT systems are typically built upon a sequence-to-sequence, or say-to-sec architecture. Conceptually, this consists of two main neural network components working together. First, there's the encoder.
What does the encoder do?
This network reads the input sentence in the source language word by word or token by token and compresses its entire meaning and context into a set of numerical vectors. You can think of it as creating a rich, dense summary or representation of the source sentence's meaning. A thought vector, some called it early on.
Okay, so it encodes the meaning, then the decoder.
Then there's a decoder. This network takes those context vectors produced by the encoder and begins generating the translated sentence in the target language, one word or token at a time. The generation is autoregressive.
Meaning it uses what it just wrote to figure out the next word.
Precisely. Each word it produces is fed back as input to help predict the next word in the sequence, ensuring grammatical and semantic coherence in the output translation.
I can imagine how trying to condense an entire sentence, especially a long or complex one, into a single fixed thought vector could be a bottleneck, though. You might lose details. How did they solve that challenge of retaining all the necessary information?
That's an excellent point, and it leads directly to the critical innovation of the attention mechanism. A major limitation of the basic encoder-decoder model was indeed this information bottleneck, where a single fixed-size vector struggled with very long sentences. It couldn't remember everything.
So attention helps it focus.
Exactly. The attention mechanism elegantly solves this by allowing the decoder at each step of generating a word in the target language to look back and pay selective attention to different relevant parts of the original source sentence.
Dynamically.
Yes. For example, when translating a French sentence into English to generate the first English word, the decoder might focus its attention heavily on the first few words of the French sentence. But to generate a later English word, it might intuitively shift its attention to a completely different part of the source text that's relevant to that specific word.
That's clever. It's like the machine is focusing its gaze where it matters most for the current word, just like a human translator would, intuitively linking concepts across languages.
Exactly right. This allows the model to dynamically focus on the most relevant source information for each step of the translation process, preserving crucial details and handling differences in word order and structure between languages much more effectively.
This attention mechanism is a major reason why modern machine translation feels so accurate and fluent compared to older methods. It's not just translating words, it's translating meaning by focusing attention.
Precisely. And the advancements in NMT, largely thanks to attention and architectures like the Transformer, have truly made high-quality, real-time translation a ubiquitous technology that we often take for granted. It's the powerful engine behind services like Google Translate and Microsoft Translator, seamlessly integrated into web browsers, social media platforms, and our everyday communication tools.
The societal and economic impact of this ubiquitous real-time translation is absolutely profound, isn't it?
It really is. NLP-powered translation directly breaks down language barriers, fostering global communication and collaboration for individuals, businesses, researchers, and tourists alike.
And for businesses.
For companies, it enables the rapid and cost-effective localization of products, websites, and marketing materials, significantly accelerating their entry into international markets. It also allows for the provision of multilingual customer support without needing large, expensive teams of human translators, thereby reducing operational costs and dramatically improving the global customer experience.
It's incredible to think about how much easier it is now to travel, research, or connect with people globally, thanks to these tools right in our pockets or browsers. This isn't just about convenience. It truly has changed how we interact with the world and flattened geographical barriers in many ways. We've talked about understanding and generating language and translating it across cultures. Now let's explore how NLP can actually quantify something as subjective as opinion through sentiment analysis. This seems critical in an era dominated by user-generated content reviews, social media posts, where everyone has a platform.
You're right. Sentiment analysis, often called opinion mining, is the NLP task specifically dedicated to systematically identifying, extracting, and quantifying the emotional tone and subjective opinions expressed within text. It allows organizations to move beyond simply collecting data to truly understanding the underlying feelings and attitudes behind it. It's about getting the vibe from text computationally.
So how do machines actually do this? What are the methodologies they use to gauge emotion or opinion from words? It sounds tricky.
The approach has evolved quite a bit over time. The most straightforward and the oldest is the rule-based or lexicon-based approach.
Using dictionaries of positive and negative words?
Essentially, yes. This uses a pre-compiled dictionary, a lexicon, where individual words are assigned a sentiment score. For example, excellent might get a +1, terrible gets a -1, and neutral maybe gets a 0. The system then analyzes text by simply counting occurrences of these positive and negative words, maybe applying some simple rules for negation like not good, to compute an overall sentiment score for the text.
That sounds transparent. You can see how it works, but also maybe a bit rigid, like it could easily miss subtlety or sarcasm.
It is transparent, but it's also quite brittle, as you say. It struggles significantly with context. The word sick could be bad, or it could be good slang depending on context. It struggles with the sarcasm. Imagine trying to analyze, "Great, another meeting," said sarcastically, using just word scores.
Right. It would probably score that as positive.
Exactly. And it struggles with nuance, which can easily invert the polarity of a statement. This is why the machine learning approach is dominant today.
Learning from examples again.
Yes. Instead of relying on predefined rules and dictionaries, machine learning models are trained on very large data sets of text that have already been labeled with their corresponding sentiment. Think thousands, millions of product reviews paired with their 1 to 5 star ratings. By processing this labeled data, models learn complex patterns, word combinations, and contextual cues that humans use to express positive, negative, and neutral sentiments. They learn what patterns signal opinion.
So it's not just counting individual words, it's learning how words are used together in context to express sentiment, almost like reading between the lines computationally.
Exactly. This allows them to classify new, unseen text with significantly higher accuracy and a much better grasp of context than simple lexicon-based systems. Many modern systems even employ a hybrid approach, combining the explicit rules of lexicons for common cases with the powerful pattern recognition capabilities of machine learning for more complex situations, getting the best of both worlds.
You can think of it as the difference between a simple spell check for emotions and a deep literary critic who understands subtext and tone. That's the leap in sophistication we've seen.
That analogy perfectly illustrates the jump. And I hear modern sentiment analysis goes far beyond just bucketing things into positive, negative, or neutral. What kind of granularity are we talking about now? How detailed can it get? It's much more refined today. Modern sentiment analysis offers a far more granular understanding. We have fine-grained sentiment analysis, which classifies sentiment along a more detailed scale, like mapping directly to a 1 to 5 star rating system, or using categories like very positive, positive, neutral, negative, very negative to measure the intensity of the sentiment.
Okay, measuring strength.
But what's particularly powerful and commercially valuable is aspect-based sentiment analysis, or ABSA.
What's ABSA? That
Yeah.
sounds incredibly specific, like sentiment about parts of something.
Exactly. ADSA drills down to identify the sentiment associated with specific aspects or features of a product, service, or topic being discussed. For example, if you read a review that says, "The camera on this phone is amazing, but the battery life is disappointing,"
Right.
a simple overall sentiment analysis might classify it as neutral or mixed. In contrast, ABSA would pinpoint a positive sentiment specifically for the camera aspect and a negative sentiment specifically for the battery life aspect. This provides incredibly specific, actionable feedback to businesses.
That's incredibly useful. It's not just, is the review good or bad,
Mm-hmm.
but what exactly is good or bad about the product, and why are people feeling that way?
Mm-hmm.
That level of detail is a massive aha for companies trying to improve.
Exactly. Beyond that, there's emotion detection, which aims to identify specific human emotions like joy, anger, sadness, fear, or frustration, providing a richer psychological profile of the text's author. And also intent analysis, which focuses on identifying the user's underlying intention, distinguishing, for instance, a casual question about a product from an actual intent to purchase it.
So how do businesses actually use this voice of the customer understanding derived from sentiment analysis in market intelligence? Where is it applied in the real world?
This is sentiment analysis's primary application area, understanding customers at scale. For example, in social media monitoring, brands use sentiment analysis tools to track conversations about them on platforms like Twitter, Facebook, Reddit, blogs, news sites in real time.
What does that let them do?
This allows them to quickly gauge public reaction to marketing campaigns, product launches, or news events. By rapidly identifying spikes in negative sentiment, they can proactively manage potential PR crises before they escalate. Conversely, they can amplify positive trends and engage directly with satisfied customers or influencers.
That's a critical tool for public relations and marketing, almost like an early warning system. What about for product development itself? Can it help make better products?
Definitely. For product and service improvement, companies systematically analyze customer reviews from e-commerce sites like Amazon, app stores, support tickets, survey responses. Aspect-based sentiment analysis is particularly invaluable here, as it can pinpoint exactly which features of a product are consistently causing frustration or delay.
So they know what to fix or what to double down on.
Precisely. This data-driven feedback loop directly informs product development priorities, helping businesses refine their offerings to better meet customer needs based on actual user feedback, not just guesswork. Beyond that, sentiment analysis is increasingly used in market and political research to track broader market trends and public opinion. Financial firms analyze sentiment towards stocks or economic indicators. Political campaigns gauge public opinion on issues and candidates to shape messaging and strategy.
So every review you write, every comment you post online, can potentially contribute to a massive data set that businesses and organizations use to understand and react to public sentiment, directly influencing the products and services you use. That's a powerful thought. Knowing your individual feedback, aggregated with millions of others, is being listened to and acted upon by machines.
As we've seen, the transformative power of natural language processing extends far beyond just those consumer-facing applications like chatbots or translation. In specialized data-intensive industries, NLP is becoming an absolutely indispensable tool for unlocking insights from vast quantities of unstructured text, driving efficiency, mitigating risk, and enabling entirely new capabilities that were frankly impossible just a few years ago.
Let's start with healthcare. It's an industry known for generating colossal amounts of data, with some estimates saying around 80% of it is unstructured, trapped in clinical notes, discharge summaries, doctors' dictations within electronic health records, EHRs. NLP, it seems, is the key to unlocking this treasure trove of potentially life-saving information.
It absolutely is. One primary use case is clinical documentation and summarization. NLP systems can parse unstructured clinical notes to automatically extract critical information like diagnoses, symptoms, medications prescribed, lab values, allergies.
All the key facts buried in the narrative.
Exactly. And use this to populate structured fields in electronic health records or generate concise summaries for physicians. This drastically reduces the administrative burden on clinicians, a major contributor to burnout, while also minimizing data entry errors and allowing physicians to spend more precious time on direct patient care.
And speech recognition helps here too, right? Dictation.
Hugely. Speech recognition technology, which is powered by NLP, dramatically streamlines dictation, allowing doctors to speak their notes and have them turned into structured, searchable text almost instantly.
So NLP can also enhance clinical decision support for doctors, helping them make better decisions.
Yes. Clinical decision support, CDS systems, are significantly enhanced by NLP. It extracts relevant, patient-specific information from the narrative text in their records details that might be missed in structured data and cross-references it with the latest medical literature and guidelines.
To provide alerts.
Right, to provide timely, evidence-based alerts and recommendations, such as flagging potential adverse drug interactions based on the patient's current medication list extracted from notes, or suggesting appropriate treatment protocols based on symptoms described. NLP also enables more sophisticated predictive analytics and phenotyping.
Phenotyping? What's that?
Phenotyping is grouping patients based on complex observable traits, often combining multiple data points. NLP boosts this by extracting rich details like specific symptoms, disease progression markers, lifestyle factors, and even social determinants of health from clinical notes. This enables powerful research into conditions like Alzheimer's or identifying patients at high risk for certain outcomes. Some studies even use NLP on social media posts carefully and ethically to identify language patterns that might predict risks like suicide.
Wow. And it speeds up clinical trials, which is huge for developing new treatments and getting them to patients faster. How does it do that?
Clinical trial matching automates the incredibly laborious recruitment process. Instead of research coordinators manually sifting through potentially thousands of patient charts,
Which must take forever.
NLP algorithms can scan electronic health records to automatically identify individuals who meet the complex, often very specific, eligibility criteria for ongoing clinical trials. This dramatically accelerates new treatment development and gets crucial therapies tested and potentially approved more quickly. In essence, the aha here is that NLP is driving more efficient, accurate, and potentially life-saving healthcare, directly benefiting both patients and medical professionals by making sense of the text data.
Moving to finance, another data-heavy field. It's an industry that operates on a constant, overwhelming flow of unstructured text. Financial news, social media chatter, analyst reports, corporate filings like 10-Ks, customer communications. NLP must be absolutely critical for real-time processing here.
It is increasingly so. In market analysis and algorithmic trading, sentiment analysis is a key tool, as we discussed. NLP models rapidly scan news headlines, earnings call transcripts, regulatory filings, and even social media feeds to gauge market sentiment towards specific stocks, bonds, or entire sectors.
And use that sentiment to trade.
This real-time sentiment data can then be used as a powerful input signal in algorithmic trading strategies, enabling firms to make complex buy or sell decisions in milliseconds, often reacting to news or sentiment shifts before human traders can even fully process the information.
That's high-stakes application right there. What about fraud detection, which is such a huge problem in cost and finance?
NLP is proving to be a powerful new weapon against financial fraud. By analyzing text from emails, chat logs between customers and banks, and even transaction descriptions, algorithms can detect subtle linguistic patterns and anomalies indicative of fraudulent activity.
Like what kind of patterns?
Things like the language used in social engineering attacks, phishing attempts, or inconsistencies in communication patterns. This significantly reduces false positives compared to traditional rule-based fraud detection systems and enables much faster detection, potentially preventing millions in losses. Investment banks and credit card issuers are using this quite extensively.
And for compliance. All those regulations.
And for risk management and compliance, NLP automates the review of dense legal and regulatory documents. It can extract key risk disclosures, identify non-standard liability clauses in contracts, and monitor regulatory changes across jurisdictions automatically. JP Morgan's Koyon platform Contract Intelligence is a famous example. It uses NLP to analyze commercial loan agreements in seconds, a task that previously took lawyers and loan officers an estimated 360,000 hours annually.
360,000 hours. That's astonishing efficiency. So NLP is influencing everything from our investments to the security of our bank account and the stability of the financial system. It's a silent guardian, or maybe a silent analyst, in the financial world.
Absolutely. And the legal profession, too, fundamentally revolves around the interpretation and creation of massive volumes of text contracts, case law, statutes, evidentiary documents. NLP is automating and augmenting many historically manual, time-consuming, and frankly expensive tasks in legal tech.
Like electronic discovery in litigation.
Right.
Sifting through millions of electronic documents sounds like an absolute nightmare and incredibly costly for clients.
It is. Electronic discovery, or e-discovery, traditionally involves armies of paralegals and junior lawyers manually reviewing documents. NLP helps automate this by employing text classification to categorize documents by relevance or privilege, topic modeling to identify key themes across vast data sets, and named entity recognition to extract important people, places, and dates. This drastically reduces both the cost and the time required for discovery, making litigation potentially more accessible.
And reviewing contracts, that seems like a perfect fit.
For contract analysis and review, NLP-powered tools automatically review legal contracts to extract key clauses. Think about liability, termination, payment terms, identify non-standard or potentially risky language compared to templates, and check for missing provisions. This significantly accelerates critical due diligence processes in complex corporate transactions like mergers and acquisitions.
And for legal research itself, I imagine it goes way beyond simple keyword searches now, finding relevant past cases.
Indeed. Traditional keyword searches are often imprecise in legal contexts. You miss relevant cases or get swamped with irrelevant ones. NLP-powered legal search engines use semantic search capabilities to understand the conceptual meaning or the legal issue behind a lawyer's query.
So it understands the idea, not just the words.
Exactly. This retrieves far more relevant case law and precedents. Some advanced systems are even attempting to analyze patterns in past judicial rulings to predict potential case outcomes, though that's still an emerging and debated area. The profound impact here is making legal processes faster, more affordable, and potentially more consistent by transforming manual document review into efficient, automated analysis.
Finally, let's look at manufacturing. This might seem like a world of physical machinery and supply chains, perhaps less text-heavy. But there must be a vast amount of unstructured text data hidden in places like maintenance logs, quality control reports, and supplier communications.
That's precisely where NLP shines, often in surprising ways. Predictive maintenance is a flagship NLP application here. It analyzes free text notes entered by technicians in maintenance logs, things like machine making unusual vibration, faint metallic odor detected near bearing, filter seems clogged again.
Notes of the human rights?
Exactly. NLP identifies linguistic patterns in these notes that often precede equipment failure. This allows companies to shift from reactive or scheduled maintenance to proactive, condition-based maintenance, scheduling repairs before a breakdown occurs. This can significantly reduce costly, unplanned downtime, potentially by 30–50% in some cases, a huge aha for any factory manager running tight schedules.
That's a huge cost saving right there, preventing breakdowns. What about quality control in the factory? Can NLP help find the root cause of problems?
Yes. For quality control, NLP aids immensely in root cause analysis of issues. By analyzing text from inspection reports, customer complaints filed online, and operator notes from the production line, manufacturers can quickly identify trends in product defects, like recurring issues with a specific component or process, and trace them back to specific production line problems, or even specific shifts or machines. This enables faster corrective action and helps prevent future quality issues.
And the supply chain, all those orders and invoices.
And in supply chain optimization, NLP automates the processing of unstructured documents like purchase orders, invoices, shipping manifests, and even emails between suppliers and buyers. It extracts key data like quantities, delivery dates, and product codes automatically. It can even analyze the sentiment of supplier communications, like emails expressing concern about delays for early warnings of potential disruptions, enabling more resilient and efficient supply chain management.
So this really shows how NLP's reach extends far beyond what might seem obvious, even touching the efficiency of factories and the flow of the physical goods you buy every day. It's truly an unseen force in modern industry, optimizing processes through text. We've covered the amazing applications, and the sheer breadth is stunning. But as you said at the top, NLP is not a solved problem. There are significant roadblocks, especially given the inherent complexity of human language itself. It's not a neat logical system for a computer to handle easily.
That's right. The most fundamental obstacles stem from the very nature of language itself. Unlike the structured, unambiguous languages of mathematics or computer programming, human language is incredibly fluid, dynamic, and deeply contextual. The single greatest and most persistent challenge is, arguably, ambiguity. It manifests at practically every level of language processing.
Can you give us some clear examples of these different types of ambiguity that trip up NLP systems? How does ambiguity actually show up?
Certainly. First, we have lexical ambiguity, also known as polysemy. This is simply where a single word has multiple distinct meanings. For instance, the word bat can refer to a piece of sporting equipment or a flying mammal. The word bank can be a financial institution or the side of a river. Without sufficient surrounding context, a machine has no inherent way to determine the intended sense or meaning.
Okay, word meaning ambiguity. What else?
Then there's syntactic ambiguity, sometimes called structural ambiguity. This arises when a sentence can be grammatically parsed or structured in more than one valid way. The classic example often cited is, I saw the man with the telescope.
Right, who has the telescope? Me or the man?
Exactly. This could mean the speaker used a telescope to see the man, or that the speaker saw a man who was holding a telescope. The sentence's grammatical structure itself is open to multiple interpretations.
And then there's semantic ambiguity, where the words themselves are grammatically correct and individually clear, but the overall meaning of the sentence is still open to interpretation by humans, even if the structure is clear.
Exactly. A common example is visiting relatives can be annoying. This could mean either that the act of you visiting your relatives is annoying for you, or that relatives who come to visit you are annoying to you. It's hard to tell the intended meaning without more context about the speaker's feelings or the situation.
Okay, ambiguity is a massive hurdle. What about nuance? Sarcasm, idioms.
Beyond ambiguity, NLP models consistently struggle with nuance. Human communication is incredibly rich with sarcasm, irony, idioms, kick the bucket, metaphors, time is money, and cultural references, where the literal meaning is intentionally different from the intended message. A sarcastic, "Oh, that's just great," expresses the exact opposite of its literal sentiment, a distinction that purely statistical models trained on literal meaning often fail to capture without much deeper world knowledge or contextual understanding.
And this all points back to context dependence, doesn't it? Our language is so fundamentally intertwined with who we're talking to, where we are, what happened before, and what we both already know about the world.
Precisely. All human language is deeply context dependent. Meaning is shaped by the preceding conversation, the relationship between speakers, are they friends, boss employee, the physical setting, and a vast amount of shared cultural knowledge and common sense reasoning. While modern models like transformers are much better at capturing local context within a document or a short conversation,
They still struggle with the bigger picture.
they still often lack the deep, common sense reasoning and extensive world knowledge that humans use effortlessly to navigate complex conversational and social contexts over longer periods or involving real world understanding. The core difficulty, the big aha here for us, is that human language is incredibly fluid and dynamic, built on unspoken rules and shared understanding that is very, very hard to formalize or capture completely for a machine.
Beyond these inherent linguistic challenges, which are tough enough, there are also significant practical hurdles related to data and computation, which are fundamental for building and training these powerful modern models.
These are major real-world hurdles for anyone building NLP systems today, from startups to big tech. Modern NLP models, especially deep learning ones, are critically dependent on the quality and quantity of training data. Creating large, high-quality, and accurately annotated data sets, meaning data labeled by humans, is incredibly expensive, very time-consuming, and requires significant human labor, often with specialized domain expertise. This availability of good data is often a major bottleneck in developing new applications or improving existing ones.
And even with vast amounts of general data, like scraping the web, there's an issue with applying models trained on that general text to specialized fields, right?
Right.
Like medicine or law.
Yes, that's the challenge of data sparsity and domain specificity. Models trained on general web text often see their performance degrade significantly when applied directly to specialized domains like legal documents or medical notes.
Why is that?
Because these fields have unique vocabularies, jargon, specific syntax patterns, and underlying concepts that are sparsely represented or used differently in general training data. Adapting these powerful pre-trained models to new domains, a process known as domain adaptation, is a non-trivial challenge that often requires creating entirely new domain-specific labeled data, which brings us back to the cost and effort problem.
And then there's the elephant in the room.
Yeah.
Computational cost.
Mhm.
The trend toward ever larger language models, billions, even trillions of parameters, brings an astronomical increase in the computing power needed to train them.
It's immense. Truly staggering. Training a state-of-the-art large language model from scratch is an undertaking generally reserved for only a handful of the world's largest tech corporations and well-funded AI labs.
Why? What does it take?
It requires massive clusters of thousands of high-end GPUs, specialized processors, running continuously for weeks or even months. The estimated cost for a single full training run for a frontier model can range from tens to potentially hundreds of millions of dollars, factoring in hardware, energy, and engineering time.
Hundreds of millions for one model training run. Wow.
This immense computational cost creates a significant barrier to entry for academic research labs, startups, and smaller organizations. It understandably raises concerns about the centralization of power in AI development and research, as only a few players can afford to operate at that scale.
So this is why you primarily hear about the biggest cutting-edge AI breakthroughs from a few very large tech companies. They are often the only ones who can afford the sheer computational power required to truly push these frontiers. It's a stark reminder of the practical economic realities behind the AI magic we see. With such immense power and integration into society, NLP also inevitably steps into a realm with significant societal implications and ethical considerations. These systems aren't neutral tools operating in a vacuum, and it's important to understand the broader impact they can have.
That's a crucial point for any discussion about advanced AI, especially NLP, which deals directly with human communication. One of the most pressing ethical concerns in NLP is the issue of bias. Models trained on vast amounts of internet text inevitably learn and internalize the societal biases related to gender, race, religion, age, disability, and so on that are unfortunately present in that data.
So the bias isn't an accidental bug, it's learned.
In many cases, yes, it's a learned feature derive from the statistical patterns they observe in the text they are trained on. For example, if the word doctor is overwhelmingly associated with male pronouns and nurse with female pronouns in the training data, the model will learn and likely perpetuate this stereotype in its own generated text or classifications.
And this learned bias can lead to really harmful real-world consequences, can't it? Especially in sensitive applications like hiring or loan applications.
Absolutely. In high-stakes applications, this learned bias can have direct, discriminatory negative outcomes. For instance, an AI resume screener might systematically downrank qualified female candidates for engineering roles if its training data reflected historical underrepresentation. A loan application system could show bias against certain racial backgrounds if trained on biased historical lending data. Or machine translation might inappropriately gender stereotype a sentence that was neutral in the original language.
So how do we deal with that? It sounds incredibly complex to untangle bias from useful patterns.
It is incredibly complex, and frankly, it's a very active and ongoing area of research across the entire AI and NLP field. There's no single silver bullet. Strategies being explored include data curation, which involves actively trying to create more diverse, balanced, and representative training data sets, though that's hard to do perfectly at scale. There's algorithmic debiasing, developing techniques to try and counteract biased associations within the model's internal representations during or after training. And fairness-aware training, incorporating specific fairness metrics directly into the model's training process to penalize biased outcomes.
And checking the models afterwards.
Yes, rigorous auditing and evaluation of models for biased behavior across different demographic subgroups, both before deployment and continuously afterwards, is becoming standard practice, or at least best practice. The crucial insight for us is that NLP systems are not neutral mirrors. They reflect and can amplify the data we feed them. Ensuring they reflect a fair and equitable world requires continuous effort and vigilance.
And speaking of data, NLP's immense data hunger also raises significant data privacy concerns, especially with so much personal, sensitive information being processed in emails, messages, health records.
Indeed. NLP systems often process highly sensitive personal information contained in our private communications or records. This inherently creates significant privacy risks if not handled properly. Beyond simple data breaches, where raw data is exposed, a key concern is inference risk.
Inference risk, what's that?
This is where an NLP model, through its analysis of language patterns, can infer sensitive personal attributes about an individual like their potential health status, political affiliation, or sexual orientation, even if that specific information was never explicitly stated in the text they provided. It's about what the model can deduce or predict about you based on how you write or speak.
So it's not just about protecting the data that's obviously sensitive, but what can be figured out from seemingly innocuous data, even implicitly. That's a subtle but powerful privacy consideration.
Precisely. Protecting privacy in the age of NLP requires a privacy by design philosophy where safeguards are built into systems from the ground up, not bolted on as an afterthought. Key technical strategies being developed and deployed include data minimization, a principle of collecting and storing only the data that is absolutely necessary for the task. Anonymization and pseudonymization techniques, which often use NLP itself, like NER, to automatically identify and redact or mask personally identifiable information, PII, before the main processing happens.
And encryption.
Standard encryption to protect data both when it's being transmitted and when it's stored. Increasingly, advanced privacy-preserving machine learning techniques are being explored. Things like differential privacy, which adds carefully calibrated statistical noise to data or results to protect individual identities while still allowing aggregate analysis. And federated learning, which allows models to be trained on decentralized data, for example, directly on users' own devices without the raw, sensitive data ever leaving their device or being sent to a central server.
It's a powerful thought that every word you type or speak to an AI could potentially reveal something about you, making privacy and NLP a critical frontier that continues to evolve alongside the technology's capabilities.
And the widespread adoption of NLP also brings broader societal concerns that extend beyond individual privacy. A major one today is misinformation and disinformation. The same powerful generative capabilities that allow large language models to write impressive poems or code can also be used, unfortunately, to mass-produce highly realistic and convincing fake news articles, propaganda, personalized spam, and sophisticated phishing emails at an unprecedented scale.
The potential for malicious actors to use these tools to sow societal discord, influence elections, commit fraud, Seems like a major societal threat we're actively grappling with.
It absolutely is. And then there's the impact on jobs and employment. This is a complex, two-sided coin.
Displacement versus augmentation.
Exactly. There's certainly a displacement risk for some roles. The automation of routine cognitive text-based work tasks involving data entry, basic customer service responses, summarizing documents, some paralegal document review is undoubtedly impacting the labor market. Some economic reports, like one from Goldman Sachs a while back, have estimated that generative AI could potentially automate tasks equivalent to hundreds of millions of full-time jobs globally over time.
That's a huge number. But what's the other side?
However, it's equally important, perhaps more so, to see NLP as a powerful augmentation tool. It can significantly enhance the productivity of professionals like doctors, lawyers, software developers, writers, researchers by handling tedious research, documentation, drafting, and data analysis tasks. This potentially frees them up to focus on higher value strategic thinking, creativity, and complex problem solving that requires human judgment.
And it might create new jobs, too.
It's also creating entirely new job categories, such as AI specialists, prompts engineers who specialize in crafting effective inputs for LLMs, AI ethics officers, and data annotators, who are crucial for training these systems. The future of work will likely be characterized by a significant shift in required skills and a new dynamic of human-machine collaboration rather than just wholesale replacement.
So it's a complex picture of disruption and opportunity, and it all points to an urgent need for broader societal discussions and clear frameworks for how we ethically develop and deploy these powerful language tools.
Absolutely. The profound societal impact of NLP technologies underscores the urgent need for robust ethical guidelines, industry standards, and potentially government regulations. Ensuring principles like transparency, fairness, accountability, and privacy cannot be left solely to the developers or market forces. It truly requires a multi-stakeholder effort involving researchers, companies, policymakers, educators, and the public to shape a responsible future for this technology. How do we balance innovation with responsibility?
That's a powerful question to consider as we look ahead. So what's next for NLP? What does the future trajectory of this rapidly evolving field look like, beyond the already impressive capabilities we see today?
The field is evolving at a breakneck pace. It feels like weekly sometimes. And while the dominance of large language models certainly sets the current stage, several key trends are shaping the next frontier, pushing towards even more capable, more transparent, and more integrated AI systems. One of the most exciting frontiers is definitely multimodal NLP.
Multimodal, meaning more than just text.
Exactly. Moving beyond just processing text or speech in isolation to systems that can process, understand, and integrate information from multiple data types or modalities, simultaneously so, combining text with images, audio, video, maybe even sensor data in the future.
This sounds like it's trying to mirror how humans understand language and the world, doesn't it?
Yeah.
Our comprehension is constantly enriched by all sorts of visual and auditory cues from our environment, not just the words themselves.
Precisely. This approach aims to build AI systems that can understand and interact with the world in a more holistic, grounded, human-like way. We've already seen pioneering models like OpenAI's CLAP, which learns powerful connections between images and text descriptions, and models like DALE-E or Stable Diffusion.
What can these multimodal models do?
These models enable remarkable new capabilities, such as text-to-image generation, creating novel, often stunningly realistic or creative images purely from natural language descriptions, like an astronaut riding a horse on the moon in a photorealistic style, or visual question answering, VQA, where the model can answer questions about the content of an image, like what color is the car parked in front of the house in the picture, and also image captioning, automatically generating relevant descriptive text for an image.
This integration sounds like it creates richer, more context-aware, and fundamentally more sophisticated AI systems that can interact with the world in a truly new and more useful way.
It absolutely does. Another critical area of research, especially for building trust and enabling safe deployment, is explainable AI, or XAI, which directly addresses the black box problem we talked about earlier.
The fact that we don't always know why these big models make the decisions they do.
Exactly. A major drawback of modern deep learning NLP models is their inherent opacity. As they grow in complexity with billions of parameters, their internal decision-making processes become increasingly difficult for humans to understand or trace. This creates a significant barrier to trust, especially in high-stakes applications like medical diagnosis or financial lending.
So XAI's goal is to open up that black box, shine a light inside, and provide insights into the model's reasoning, making it less of a mystery.
Exactly. Research in XAI is dedicated to developing techniques to make these opaque models more transparent and interpretable, providing actionable insights into how or why a model arrived at a particular output or prediction.
What kind of techniques does XAI use for NLP?
Key XAI techniques being applied in NLP include attention visualization. In transformer models, as we discussed, attention mechanisms assign weights to input tokens based on their perceived importance for the task. Visualizing these attention weights, perhaps as a heat map over the input text, can reveal which words the model paid the most attention to when making a prediction, offering crucial clues to its reasoning. There are also feature attribution methods that try to assign an importance score to each input feature, each word or token, based on how much it contributed to the final output. Prominent methods include LLM and Eshepo.
This seems so important for building user trust, especially in critical fields. Imagine a doctor relying on an AI recommendation for a diagnosis. XAI could potentially explain why the AI made that specific recommendation, highlighting the evidence it used, which builds trust and allows for crucial human oversight and verification.
It's crucial not only for building user trust, but also for effectively debugging models when they make mistakes, identifying and mitigating hidden biases, ensuring compliance with regulations that might require explainability, and ultimately improving overall model robustness and reliability. Finally, looking ahead, the continued evolution of large language models themselves remains the dominant trajectory. The paradigm of large, pre-trained language models will continue evolving rapidly.
Bigger and better. Or there are other directions.
Both, potentially. But a significant trend is towards domain specialization. While general-purpose models are powerful, we're seeing more development of models specifically fine-tuned on vast amounts of domain-specific data for finance, like Bloomberg GPT, for law, for medicine, for scientific research to achieve even higher accuracy, reliability, and nuanced understanding within those specialized areas. They become experts in a niche.
And we can expect even more enhanced capabilities from these LLMs in general. What might they be able to do next?
Definitely. Future models are expected to possess greater emotional intelligence, moving beyond simple positive-negative sentiment analysis to understand a wider spectrum of human emotions and potentially respond with more empathy and appropriate tone, though that's a tricky area. We'll likely see improved dialogue management, enabling longer, more coherent, and much more context-aware conversations that can span days or remember past interactions better. And there's a massive ongoing push for greater multilingualism.
Supporting more languages.
Yes, with ambitious projects like Google's Universal Speech Model aiming to support over 1,000 languages in a single model, the goal is to truly make powerful NLP accessible globally, breaking down language barriers on an unprecedented scale.
That's a huge step towards true global communication and understanding. And what about few-shot and zero-shot learning? That sounds remarkable. The idea of models doing things they weren't explicitly trained for.
It is a remarkable capability and a key feature of modern LLMs. It's their ability to perform new tasks with very few training examples, few-shot learning, or sometimes even no specific examples at all, zero-shot learning, relying solely on the broad knowledge and patterns acquired during their extensive pre-training.
How is that useful?
This is absolutely crucial for applying NLP quickly to novel tasks or in domains where getting large labeled data sets is difficult, time-consuming, or prohibitively expensive. It makes the models much more adaptable. The unfolding revolution of LLMs is really still in its early stages, relatively speaking, and their capabilities will likely continue to expand in unexpected and incredibly powerful ways in the coming years.
We've certainly journeyed through the dynamic and rapidly evolving field of natural language processing today. We went from its theoretical beginnings with those symbolic, rule-based systems
to the data-driven statistical revolution that made NLP practical at scale.
and now to the powerful neural architectures and large language models that define our present and are reshaping our digital world. You've seen how NLP silently powers the conversational assistants in our homes and phones.
How it truly breaks down language barriers across the globe through machine translation.
And how it provides critical, actionable insights to professionals in fields as diverse as medicine, finance, law, and even manufacturing by making sense of unstructured text.
But, as we've emphasized, while NLP grants machines these unprecedented abilities to understand and generate our most human data, our language, This immense power is not without its significant challenges and perils.
Right. We've explored the fundamental difficulties posed by inherent language, ambiguity, and nuance.
The very practical hurdles of needing vast amounts of high-quality data and immense computational power.
And the profound societal and ethical imperatives we face around issues like algorithmic bias reflecting societal inequalities, ensuring data privacy, combating misinformation generated at scale, and navigating the complex future of employment in an age of automation.
The future of NLP will ultimately be defined not just by how effectively machines can process words or how big the models get, but by how wisely and responsibly we, as a society, choose to guide their development and deployment.
It seems the path forward points toward potentially a deeper synthesis, combining the power of large-scale machine learning with the nuanced understanding of language structure and human cognition offered by fields like linguistics and cognitive science, getting the best of both worlds.
And perhaps a final thought for you, our listeners. As you interact with AI in your daily life, whether it's asking your smart speaker a question, using a translation app, seeing automatically generated summaries, or interacting with a customer service bot, consider this. How much more human-like will our technological conversations become in the years to come? And crucially, what responsibilities do we all have as this incredible evolution of communication technology unfolds around us?
It really isn't just about building smarter machines anymore. It's about shaping the future of communication itself and doing so thoughtfully. Thank you for joining us on the Deep Dive.